In this video, I'll be solving problem 1.61 from Griffiths' Introduction to Electrodynamics. So the problem asks us to prove 5 corollaries, mostly to the divergence theorem. Part A asks us to prove that the integral of the gradient of a scalar function over a volume is equal to the integral of the same scalar function over a closed surface. So we'll prove this by the divergence theorem. If we substitute the vector t, which is the scalar function we're interested in, times some arbitrary constant vector c into the divergence theorem, the integral of the divergence of tc over the volume equals the integral over the closed surface of ct. So we'll use the product rule on the first term. Expanding gives us that the integral over the volume of the scalar function times the divergence of c plus c dot the gradient of t is equal to the divergence of tc, and then we'll leave the other part alone. And the divergence of a constant is 0, so this term disappears, giving us that the integral of, and we can also pull the constant outside of the integral. So c dot gradient t d tau equals c dot t dA. Now, cancellation is normally not valid for dot products. Recall that instead of cancellation, all we can say about two dot products that where a dot b equals a dot c is that a dot b minus c equals 0, which means either that b equals c or that b minus c happens to be perpendicular to a. But in this case, because c is arbitrary, we can just cancel the c, and then we're left with the result. Part B asks us to show that the integral over a volume of the curl of a vector is equal to the negative of the surface integral of the same vector crossed with the area vector of the surface. So we'll again prove this using the divergence theorem. So we'll substitute the vector v cross c into the divergence theorem, where c is an arbitrary constant, and v cross c is a vector, so we're allowed to do this. The divergence theorem states that the integral of the divergence of a vector, in this case v cross c, over a volume is equal to the surface integral over a closed surface of the same vector dotted with the area vector of the surface. So we'll expand this product, which gives us this, and the curl of a constant vector is also 0, so this term disappears. If we remember the commutativity of cross products, where v cross c equals negative c cross v. So this will give us, pulling out the constant, c dot the integral of the curl of v d tau equals negative the integral of c cross v dot dA. And now the distribution of dot and cross product says that that is equal to c dot v cross dA. And then we can, again, pull out the constant, v cross dA. And just like in part A, because c is an arbitrary vector, we can cancel it, leaving us with the result that was intended. Part C asks us to prove Green's identity, which is that the volume integral of... Okay, part C asks us to prove Green's identity, which is that the volume integral of t times the Laplacian of u plus the gradient of t dotted with the gradient of u is equal to the surface integral over a closed surface of t times the gradient of u dot dA. Again, we'll prove this with the divergence theorem using some vector v, which equals t times the gradient of u. The gradient of u is a vector, so v is a vector. Plugging that in gives us that the integral of the gradient of our vector v over a volume is equal to the surface integral over a closed surface of our vector dotted with dA. So the right-hand side is finished. We'll expand the product over here according to the product rule for the divergence of a scalar times a vector, which gives us that the volume integral of t times the divergence of the gradient of u, and this is just the Laplacian, plus the gradient of u dotted with the gradient of t is equal to the surface integral as before. And with that, we are pretty much done. If we rewrite it with the Laplacian, we have that the integral of t del squared u plus, and the dot product is commutative, so we'll change this to del t dot del u t tau equals the surface integral of t times the gradient of u dotted with dA. And that's it. Part D asks us to prove Green's second identity, which is that the volume integral of t times the Laplacian of u minus u times the Laplacian of t is equal to the surface integral of a closed surface of u times the gradient of u minus u times the gradient of t dot dA. So we will show this using our result from part C, and then by finding the same result, but with t and u reversed, which is fine because they are both scalar functions. Then we'll subtract equation 2 from equation 1, which gives us this messy looking thing. So because the two terms on the left are integrated over the same region, we can combine them together. And the same is true for the two terms on the right. Now the dot product is commutative, so these two terms are equivalent and cancel, which gives us the result we were trying to prove. Part E asks us to show that the integral of the gradient of a scalar function t crossed with the area vector integrated over a surface is equal to the negative of a closed path integral of the value of the scalar function. So we'll show this by using the fundamental theorem for curls and letting the arbitrary vector in the theorem v equal our scalar function times a constant vector. Substituting gives us that the curl of our vector dotted with the area over a surface is equal to the integral of our vector around a closed path bounding that surface. We'll expand this product here and also this product here. First, we'll expand this product, which gives us that, and that's going to be equal to the integral around a path of e dot t dl. We can move the scalar function from multiplying one term of a dot product to the other. The curl of a constant vector is always 0, so this term goes to 0, and we'll distribute this product so that negative c dot gradient t cross dA equals the path integral of c dot t dl. Because c is constant, we can pull it outside of both integrals, and because it's arbitrary, we can cancel it. So canceling that and moving the negative side from the left-hand side to the right-hand side gives us that the gradient of t cross dA integrated over a surface is equal to the negative path integral of t around a boundary of the surface. And that's the result we were looking for. Thanks.